So the last thing we'll talk about for this chapter is how we can tell which of these terms is going to be higher or lower in energy than others. And this is governed by a set of rules known as Hund's rules. And there are three rules involved with Hund's rules. And these are all related to the energies of these terms. So first rule is that the largest value of capital S is the most stable, meaning the lowest energy. So in general, a triplet state will be lower in energy than a singlet state, and a quintuplet state or a quartet state, right? Any largest value of S is the most stable. Second rule is that larger L, capital L, is more stable if capital S is the same. All right, and so if we have a tie, for example, if we have, say, a singlet D state and a singlet S state, like we did for carbon, the D state would be lower in energy than the S state because it has a larger value of L. All right, and then the third rule is if L and S are the same. So this is, for example, with our carbon atom, this would be our different triplet P states, right? We have triplet P2, triplet P1, triplet P0, right? L and S are the same for these three. And so J is going to be our differentiating factor here. So it depends on whether the shell is less than half filled or more than half filled. All right, so in our case of our P2 configuration, we had a case where the shell was less than half filled. And so the first part of this applies. If shell is less than half filled, the smallest J is the most stable. And if we have the opposite, if the shell is more than half full, the largest J is the most stable. Okay, so if we go back to our carbon electronic states, if I can get there, it's lagging a little bit, right? We see this play out, right? So we have a case where the shell is less than half fill. And so we have the lowest J value is the lowest energy, and this bears out with the experimental results. We have J equals 0, then 1, then 2. And these are all pretty close in energy, right? So the different L and S, if they have the same L and S value, the energies generally are pretty close to each other within a few tens of wave numbers in the case of carbon here. But when we switch from S equals 1, right? So when S changes, when we go from triplet to a singlet state, we see a very large difference in energy, and the triplet state is lower in energy than the singlet states. And then what differentiates between singlet D and singlet S is the value of L, right? So D, because L is 2, is lower in energy than S, where L is equal to 0. The final thing that I'll mention is which electronic states can, electrons move between. And this is known as the selection rules. And so the selection rules for electrons moving between different terms is that the change in capital L can be 0 or plus or minus 1. The change in S is delta S is equal to 0. So, to a first approximation, and this holds pretty well if you have few electrons. As you get to bigger atoms where there are lots more electrons, these rules break down. But things have to stay in the same, what's known as multiplicity, right? The same value of S. So triplet states go to triplet states, singlet states go to singlet states. And then the value of delta capital J is equal to 0 or plus or minus 1, with one exception. Except for the case that you can't have J equals 0 to J equals 0 transition. So you can have 1 to 1, 2 to 2, but not 0 to 0. And so this will tell you if you have an atom in a particular electronic state, with a given term associated with it, this tells you which other terms are accessible from that. So for example, to a first approximation in the carbon atom, you can't go from this triplet P state, triplet P not zero, or triplet P zero to a singlet D state with a single photon. You have to, this is what we call forbidden according to the rules of quantum mechanics. That's it for chapter 8 for multi-electron atoms. How we actually calculate these energies is using the approximation methods that we've talked about previously. And we'll get a little bit more, we talked about a little bit with the Hartree-Fock method. And there are more advanced methods that we won't get into all of that in this class, but we will talk a little bit more about that in a later chapter.